All right, well, let's go ahead and get started. So hello and welcome to Ask Echometer. My name is Carrie Ann Taylor, and along with myself from Echometer, we have Gustavo Fernandez, who will be manning the chat and assisting with the Q&A. Also, Ken Skinner, Dieter Becker, Tony Podio, and Lynn Rowland. So we really appreciate you guys taking the time to join us today. On our echometer.com homepage, there's an access to our Ask Echometer webpage. And if you'd like to go there right now, there is a Session 12 PDF documentation bundle that you can download, and there's a copy of the PDF of today's presentation, as well as 3 technical papers that Lynn is going to reference during his discussion. And then right next to that, there's a link to download the TAM examples. In that folder, you can download a file of all of the examples you'll see us work through today. So today's session is titled Net Torque Acting on a Pumping Unit Gearbox. And so with that, Lynn, I'll go ahead and turn it over to you.
Thank you, Carrie Ann. This is a presentation that evolved from a paper that we have. It's the paper that's here at the bottom, and the third paper listed is Best Methods to Balance Torque Loadings on a Pump Unit Gearbox. So a large portion of this presentation comes out of that paper. So this will be that paper is a great reference. If you're wanting to use TAM and you haven't installed TAM before on your computer, then you can download TAM from our webpage. There's the link on the screen. So we've provided 5 different types of pump units with examples of net torque that we'll discuss during the presentation. During the dynamometer session on July the 15th, the topic was dynamometer workshop, but Dr. Podio also presented how to do a counterbalance effect test. So we're going to refer to counterbalance effect for torque calculations, and we'll talk about the other 2 methods that are somewhat related. And then the last paper here that's listed on the screen is a paper that talks about using the wireless power probes, and we discussed briefly in that paper net torque calculations on the gearbox using power. So we'll talk about that during this presentation also. That's also discussed in this best method paper also. So with that, let me go on to the first slide. Now, we're going to talk about pump unit and pump unit geometry a little bit, not much, but the geometry we have we have probably between 4,000 and 5,000 pump units that have the pump unit geometry in our database, and each pump unit has its own API designation, and it's usually the API designation that defines a pump unit. The first character usually is the type, and we'll look at air balance and conventional and mark and a Rotoflex example, and then also a reverse mark example. The second number here stands for the peak torque that can act on the gearbox. So the peak torque, the maximum peak torque, that's net gearbox torque, is 320,000 for this pump unit right here on the screen. And the maximum polish rod load in hundreds of pounds is 25,600. And then the maximum stroke with the pitman arm in the far hole on the crank is a stroke length of 100 inches. So when you look at an API description, it tells you quite a bit about the pumping unit. And normally there's a tag, well, not always, but usually there's a tag on the leg of the pumping unit that you can look at and see definition of the pumping unit description. Now, when you look at the pumping unit from the side, and if you could imagine that the polish rod is in your right hand, then this diagram shows that clockwise is this rotation, and counterclockwise is that rotation, and crank angle 0 for a conventional unit is at the top. And so clockwise 90 degrees would be there, and counterclockwise 90 degrees would be over here, and that's also clockwise 270. So the direction of rotation is based on viewing the pumping unit from the side with the polish rod in your right hand, and there's other ways to discuss this. Some people say the weights fall toward the wellhead when it's going clockwise. If you look at the pumping unit from the side, then the crank that's closest to you, we'll label crank number 1. The crank on the far side, we label crank number 2. With the crank facing the wellhead, the weight on the top is master weight number 1, and master weight number 2 is on bottom. The same thing on the far crank. 1's on top, 2's on bottom for crank number 2. So that's a pretty quick, just a description of the pump unit, a name, and a little bit about identifying the weights. Now this is an example of a tag that would be on the pump unit leg, usually the leg, and it usually will have the API description here. I didn't say what the D stands for. D stands for double reduction. And a lot of pumping unit descriptions drop that now because almost all gearboxes now are double reduction gearboxes. But in the beginning, a lot of the gearboxes were single reduction, and so they wanted to put a D there to show that there's a difference between the type of gearbox that you got on the well. And somewhere in there there'll be a here it shows the gearbox torque rating, and you don't want the net torque on the gearbox to exceed that value on the upstroke or the downstroke, or anywhere during the stroke. And so that's the gearbox rating, and it's also in thousands of inch-pounds right here. And that's typically on a tag. Sometimes the pumping gearbox will have letters, the gearbox rating in letters that you can actually see embossed on the gearbox. So sometimes you may not see a tag, but you'll still be able to see the rating on the gearbox sometimes. Now this is a video that is synced with the pumping unit, and we're measuring the polish rod load in position here, and that's real time that we did that. And this is the surface dynamometer card on the. So here's the upstroke load, and then there is the downstroke load. And so with dynamometer card is part of the mechanical torque calculations. This is the stroke length here up to 100 inches for this pumping unit. And this is a load in thousands of pounds. Now, this bottom plot, this is called an analysis plot. And also notice that the pump motion, along with the polish rod motion, is in sync with this surface dynamometer card. Now, this isn't the pump card. This is something different. So when you look at this, this is the rod torque, the torque of the rods acting on the gearbox, and then the counterbalance torque in green counterbalancing the rod torque. And so the difference between the rod torque minus the counterbalance torque equals the net torque. And so what you can see is that the biggest net torque difference during the upstroke is right here. And then right here, pretty close to right there, is the biggest difference on the downstroke. And so we want to be able to match the counterbalance moment to the well, to the pumping unit, so that we minimize the torque on the gearbox. And we want the weights to be positioned in a place so that we don't cause overload anywhere during the stroke and damage the gearbox by exceeding the gearbox rating. Now, this is that same well, and we're viewing it from the side. And if you were to look at the weights here and think about the force of gravity acting on the weights, and there's a force from each of the weights going down, and then there's also a force from the crank arm, and that's what creates the counterbalance moment. And if you could walk over here and measure that at the polish rod with a load cell, horseshoe load cell, or some kind of load cell that measures the exact loads, then that would be called the effect of the weights at the polish rod. And it's called a counterbalance effect. And so that we can use the counterbalance effect if we can determine it at the polish rod to calculate the counterbalance moment that would then be used in the torque calculation. So the idea of measuring the counterbalance effect is important because it's one of the loads that we can use then to calculate the moment. Now, when you think about the rod loading, if you look at the downstroke, when the rods are falling, they weigh equal to the weight of rods in fluid, and then they help lift the weights. When the rods are falling on the downstroke, the weights are being picked up. Now, on the upstroke, when the rods are being lifted by the pumping unit, then the weight is falling, and the rods weigh the weight of rods in fluid plus the pump load. And so on the upstroke, the rod string weighs the weight of rods in fluid plus the pump load. And on the downstroke, the rod string weighs the weight of rods in fluid. And so if you're wanting to balance as close as you can, the upstroke and the downstroke load, then the effect of the weights and the cranks over here at the polish rod should be the average of the upstroke and downstroke loads. So it should be the weight of rods in fluid plus half the pump load. And so to make a balance, to minimize the amount of work that you're doing, upstroke and downstroke, to minimize the size of your motor, the size of your gearbox, the size of your pumping unit, you want to balance that upstroke and downstroke load of the rods by having the effect of the counterbalance equal to weight of rods in fluid plus half the pump load. And API said, well, you need about 6% more than this right here, but in general, it's about half. Weight of rods in fluid, about half the pump load. And so think about when you're on the upstroke, then this weighs weight of rods in fluid plus the full pump load, and this weighs, at the effect of the polish rod, weight of rods in fluid, but only half the pump load. So we're having to lift half the pump load because at 90 degrees, because this weighs half the pump load less than this load over here. Now, when the rods are falling, they're having to lift this effect of the weights and cranks of the polish rod. And so now on the downstroke, this is the weight of rods in fluid plus half the pump load, and this is the weight of rods in fluid. So now this is too heavy by about half the pump load. And we're ignoring the effects of acceleration. We'll see the effects of acceleration, and that's also in there. So anyway, the idea is that the counterbalance effect of the loads at the polish rod from the weights and the cranks should be the weight of rods in fluid, upstroke and downstroke, and then about half the pump load, so that you only lift half the pump load on the upstroke and half the weight of half the pump load on the downstroke. But now it's caused by the weights being heavier than the rod string by half the pump load. So that's kind of a long discussion. All right, so here is the peak polish rod load and the minimum polish rod load. And for a conventional unit, it's common, not always, but common for the peak torque on the upstroke and downstroke to be very close to occurring at this peak. This is called torque right here, and this is torques in thousands of inch-pounds. This is the net torque on the gearbox, and it occurs. There's a peak on the upstroke, and this is the upstroke side. This is the downstroke side, and this is the peak right here. And so when you look at this pumping unit and you watch it operate, here it's operating. So throughout the stroke, the angle here of these weights is changing, and so the counterbalance is changing, and the rod loading is different upstroke and downstroke, and there's acceleration forces here and there. And so when you look at this is a position. This unit's going counterclockwise, and so when you go counterclockwise, this is where the crank would be when the peak load occurs about 62 degrees counterclockwise. That's when the peak load occurs, and that's when the peak torque occurs on the upstroke. And then on the downstroke, then the crank would be right about here, in fact, you usually say it's at 90 degrees. Well, it's not at 90 degrees. This minimum load occurs at this point when the acceleration force from the release and the fluid load occurs right there. That's the minimum load, and that's about 250 degrees would be all the way around to 180, and then not quite 90, but 250 degrees right there. And that's the angle where the peak torque occurs on the downstroke. And if we make this peak and that peak equal, then what will happen is that the motor will see a lower average torque, net torque, and it will run a little bit faster, and it will be a little bit more efficient, and we'll see a reduction in the cyclic load factor. And the cyclic load factor is what we use to calculate the horsepower, the motor horsepower requirements. And so the cyclic load factor is the more the net torque varies, the higher the cyclic load factor is, and the more imbalanced it is, the closer to a minimum, closer to 1, the cyclic load factor would be. So ideally, when you make these two peaks the same, you have the lowest cyclic load factor, and it's the most efficient, and the least amount of energy is being wasted to heating of the motor during changing speed due to cyclic loading. Now, this is a plot of the net torque curve. So this is the net torque curve here, calculated in black and in red. The red is for mechanical torque based on the weights, and the black is for kW. And what we note here is we have 3 examples of net torque curves for motor power or for torque. And if the first peak on the left side during the upstroke is the highest, we call it rod heavy. And you can see that it's not very equal, and so the motor is going to really change speed here, trying to pick up the rods and then go fast when not picking up the weights. And so here we see that this peak on the right is less than the peak on the left, and this side is picking up the weight, so it's weight heavy. And now on this one, the peaks are balanced, which means we put the weights in the right place, and we minimize the peak torque, we reduce peak torque, we minimize the loading on the motor, and now we have a little tiny bit faster speed and more efficient operations, and we're electrically or mechanically in balance. And so when you look at your net torque curve, you look at the left side. If that left side is the highest, that's picking up the rods, you're rod heavy. If the right side is the highest, that means you're weight heavy. And if they're both close to the same height, then that means you're electrically or mechanically in balance, and your efficiency is going to be the highest for the surface equipment. All right, so we're going to talk about the 3 methods, and this is out of this paper that we referenced earlier. And Echometer provides 3 different methods to do net torque on the gearbox. One method is to measure the input power with a power probe, either wired or wireless, and that's the kW used at the same time as doing a stroke. And the kW is directly proportional to the net torque on the gearbox. So if you know the kW with some with an equation, you can then calculate the net torque on the gearbox and use the power to position the weights. Now, you can also do a CBE test. And Dr. Podio talked about that in July, how you do the CBE test. And the CBE test is you use a load cell that can actually weigh the rod string. And that whole method is talked about, and I'll talk about it a little bit, but the CBE test is a mechanical method, and the CBE is then used to calculate how much moment the weights and the counterweights and the crank provide to resist the rod torque, or to counter the rod torque. And then the third method is similar to the CBE method, but that both of them need a dynamometer card, and it's something called torque factors to calculate the rod torque. But for the third method, we have a database that has weights and cranks in it, and their weight of the crank and the weight of the weight and their center of gravity, and you tell the software how far the weights are from the end of the crank, and then that is used to calculate the inches times the pounds, and sums up to be the moment, inch-pounds of moments, like a torque wrench acting around the gearbox shaft, and then that is calculated the rod torque minus the counterbalance moment, and that gives us a net torque. So those are the 3 different methods that we use, and we'll talk about each of these in the coming slides. Now, this is just a picture kind of trying to show that there's 3 methods. And the CBE method has an arrow here saying that you were able to hold this crank level and balance the rod loading with the weight of rods and fluid plus with the pump load. That's some of the pump load slips off. You balance that load with the effect of the weights, and when you release the brake, this crank stays level for a short time. And you note that time and you identify that load, and then you know you've measured the CB load, the load that balances with the effect of the weights, and that's on the upstroke. So you're doing this test on the upstroke. And then the counterbalance moment method is you took a tape measure and measure from this point to that point for each weight, the weight number 1, weight number 2 on crank number 1, and weight number 1, weight number 2 for crank number 2, and you type those inches from the end of the crank distance from the leading edge of the weight, and then that is in, you pick the weight out of the database, and that then becomes inches from the gearbox shaft center, inches from here to the center of gravity, and we take that distance times those inches based on the inches you tell us from end of crank, and we sum all that up, and that gives us the moment, and then the moment along with the dynamometer card, and the torque factors become the net torque. And then the third method that really we call it method 1 on the previous slide is measuring the power with the power probe inside the panel. We just measure the kW, and the kW is directly proportional. It's a pretty simple method. It's easy to do as long as you have electric motor. So why do you want to do torque? Why is that important? Well, the most important reason is that the gearbox is very expensive. And if you overload the gearbox above its API rating, then its life is reduced. And so if it's way out of balance, then the speed is going to change on upstroke and downstroke. So that's one reason why you probably want to have a balance. So as it's more and more out of balance, it's going to put more and more load on the motor and tend to cause things to stall out. And it may even cause belts to break or motors to burn up if it's way out of balance, and also damage the gearbox. If you go really fast, I think the gearbox is rated for pretty high speeds. If you go really slow, you need a lubricator inside or a wiper that wipes the gear lube onto the gearbox. If you go less than 5 strokes a minute for an older style pumping unit, most of the newer style pumping units, I don't know if all of them do, have a wiper that comes with it that allows you to go at a very slow speed. Now, if you have condensation in your gearbox, that can cause damage to your gearbox. So lubrication quality is important. If you overload it, you'll get metal filings, and so periodically your gearbox should be tested. The lubrication should be tested, and if it has metal filings in it, it means you've overloaded the gearbox. If it has water in it, you need to replace it. If the gear lube is no longer quality, then you need to flush it out and replace it. Now, the next one, the full pump or pounding conditions. A lot of pumping units torque on the upstroke and downstroke kind of assume that the pump conditions aren't changing, and so when you balance the unit based on the pump being full or pump being partially filled, and then the conditions change to be different, like let's say we balance it full and then you pump it off and you start pumping most of the time with the conditions with the pump not full liquid, then the load conditions, rod load-in conditions on the downstroke significantly change, and we'll show that in some examples. And the gearbox torque dramatically changes, and so you have to be cautious about gearbox loading when you have wells that pump fillage changes, because that can cause the gearbox to fail just because the pump's not full. The prime mover. Some of the electric motors are high efficiency motors that they call NEMA B motors, and a NEMA B motor is stiff, and it tends to go at a constant speed, and when it picks up the rods, it tends to pull harder instead of slipping like the normal NEMA D motors do and reduce peak torque. And so if you have a NEMA B motor, typically you have higher peak torque, so lower minimum torque, and that's because the motor tends not to slip. And so that's one of the things about a prime mover. Now the cyclic load factor is used to, determine the horsepower required of your motor. You take the cyclic load factor times the polished rod load divided by the unit efficiency, and then that gives you the required motor size. So the higher the cyclic load factor, the higher the motor you need, the more horsepower you need, and the lower the cyclic load factor for torque, the smaller the motor you need. So the cyclic load factor is an indication of the unit not quite matching the requirement of the rod loading. The higher the cyclic factor goes, the poorer match you have. Now, counterbalance. Counterbalance, we assume the weights are in the right place and the gearbox is properly loaded, and that uh, provides a long life to the gearbox as long as the gearbox is serviced and it's maintained. If it's way out of balance with weights in the wrong place, then that can significantly reduce the life of the gearbox. So we'll talk about that more. This is a graph for gearbox life, and this came from Cecil Hunt. He was a chief engineer for Lufkin quite a while ago, and we used to talk to Cecil and say, Cecil, send us a curve that shows us how much we damage our gearbox based on overload. And he would say something like, oh, this is proprietary, it's top secret, I can't tell you. But when he retired, he sent all the people, me as one of them, that was pestering him, wanting him to send us information about the life of how the overload affected the gearbox life. And so, your gearbox life could be 25 years or more if it's properly maintained and it's loaded less than 100%. But if you loaded your gearbox 25% overload, then your life of the gearbox drops down to like 3 years. And so it can be a significant problem, and it'll keep on going until 3 years, and then it'll fall apart. So it's not an instant death if you overload your gearbox, but it's gradual. It occurs over time, and the pumping is out there forever, pumping the well. And if it's overloaded, it's going to wear out if it's prematurely wear out if you don't keep it in proper counterbalance. Now this is a permissible load diagram. This is one of the examples we have, and the examples is called gearbox balance, and we've used this example a lot. And the plot is called permissible load, and so we're making a plot of the load of the load cell, of the surface loads measured, and this is upstroke right here, this is a downstroke, and this is a marked pumping unit, and usually pumping units have a much lower minimum load than conventional units because it goes faster on the downstroke. It says that if the red dashed line is existing permissible load, and so if the black line goes above the red line, then the gearbox is being damaged due to overload. And so here on the downstroke, it's not going below the red line. And if we balance it by putting the weights in the correct place, then it won't be overloaded on the upstroke or on the downstroke. See how the counterbalance moment comes up on the downstroke, and you have to be concerned about overload on the downstroke if you move the weights out farther on the upstrokes. And so this is saying that we'll be okay if we counterbalance it so we don't overload right there, and we didn't overload now on the downstroke. It comes up, but it didn't overload. It didn't cross that line. So if you look at this, you say, gosh, that's quite a bit of overload. The report on the dynamometer report in TAM says this is a 125% loaded pumping unit gearbox, or 25% overload, and the rod's way too much. They're too heavy, rod heavy. The weights need to go out farther, and we need to move this 10,800 pounds of weights out 27 inches. And if we do that, then the gearbox is going to be loaded 96% of its rating, and the average torque loading on the upstroke and downstroke should be about a 617,000 inch-pounds. So we'll drop below the 640 gearbox rating of the gearbox. Now, since it's 125%, there's a dot right there. And so this operator that has this well, he is causing his gearboxes on this well, they would fail every 3 years if he doesn't identify the problem and correct it. So this we'll talk about this example more. So this just due to the overload that we have on this well, it's 790. Let's go backwards. It's 797,000 inch-pounds, and it's rated for 640. So it's quite a bit overload, and quite a bit out of balance. But that's causing a huge 90% drop in gearbox life because of that overload. Now, when you position the weights and properly counterbalance your unit, you're going to do two things. You're going to, if it's overloaded, you'll prevent a failure of your gearbox, which will reduce your operating expense. And if you balance it, the change in the cyclic load factor is the percentage change is the same percentage change you'll see in your power bill. So you reduce your power. You will minimize your gearbox loading and not exceed your gearbox rating. Ideally, if the pump unit is properly sized, you'll have more uniform loading on throughout your stroke, and that will contribute to more uniform speed and higher efficiency, and that'll lower your energy cost, less power, and it'll minimize your gearbox requirement size. So if you have higher torque loading, you'll need a bigger gearbox, or if you balance it, you may be able to use the existing gearbox on your well, and you'll prevent damage to your equipment. So those are some important reasons to be concerned about overloading your gearbox. Now this is the wired power probes inside the panel, and this is Rusty connecting this wired power probe, and you have two current sensors and 1, 2, 3 voltage connectors, and this device right here at the same sampling speed as the dynamometer test samples the voltage and the current and outputs the current and the kW. So it calculates the kW inside this box. And so this is the wired power probe, and you have to connect them properly, or they will not read correctly. So this has to be, these two yellow labels have to be face up, and this is toward the transformer. This is away from the motor, and this is labeled right, center, and left, and you have to connect them on some bare metal to measure and record that data. Now this is the wireless power probe, and since it has a radio in it, we designed the wireless power probe to also send us the voltage. So the wireless power probe reads the voltage and the amps and the kW, and we can use that information to see if the wire going from the pumping unit to the transformer is too small, and we're wasting energy by the cyclic loading causing current to flow back and forth between the wires. So this is an antenna, and the antenna needs to see the base station that we transmit back and forth the data from the panel back to the computer in TAM. So this is now if you aren't allowed to open the panel, then Echometer has a thing called a fixed power adapter that can replace this harness. And so you can replace this harness right here with a connection inside, and then there's a little plug on the outside, and you just plug right into that connection, and you don't have to open the panel, and you can collect the power, current, and voltage data without opening the panel. This is again the same well, the V11 well, and what I'm showing in this data here, this is an example that we have. We'll go through this. We look at stroke number 2, it's full, and then the pump fillage changes. And so as the pump fillage changes, the rod load changes, and the net torque on the gearbox changes. And so it's important when you position your weights to position the weights for the normal pump fillage. If your well is going to operate with the pump off controller and basically be full, then you would position weights on the full card. If you're going to operate on hand and the pump won't be full, then you need to position the weights based on the pump card not being full. All right, so that's what this is trying to show here. Now this is just a video that's showing how the pump fillage changes, and this is the kW right here. And so if we look, we can see the kW goes to a maximum. Let's see if we can find it. It starts going to maximum right about there, and it goes to a maximum right in here, I think. Let's look. Goes to a maximum kW right there, and it goes to a maximum kW right here near the minimum load. So the kW, this little speedometer here, is showing us the instantaneous kW during the pumping cycle, and it can tell you where the maximums occur, and typically they occur right about there near the peak, right up there near the minimum. But the torque factors have an impact on this, so it won't be quite the same as if the pump was full. We'll talk about that more. Now this is the data from that same well, and what it's showing is that this is the load versus time. This is the position from the accelerometer versus time. This is the power, and this is the upstroke and downstroke peak. So here's upstroke and downstroke. If you look right there for one stroke, that peak is smaller than that peak. That means that the downstroke peak is higher, so we are weight heavy. The weights are too far out, just by looking at the kW. This is the current, and the current doesn't go below zero. The kW does, and that where it goes below zero is where the motor is going faster than 1200 RPM, or synchronous speed, and it generates power. So during every stroke, a conventional unit typically generates power. It's generating power right there and right there, and that's when the weights fall and push the motor faster than the synchronous speed. And here is the current, and here is the voltage, and the voltage when you stop for a valve test. This is a standing valve test. So you can see that the load becomes flat. No change in position. The power drops to zero. The current drops to zero because we put our connectors below the HOA switch, and we put the voltage connectors above the HOA switch, and they're reading the power on the line, and so it jumps up to a fairly constant 480 volts. And then when we turn it back on, you can see the drop in the voltage, because the voltage has to travel from the transformer to the well. It's like a pressure drop, voltage drop. And then the current jumps up to a really high value. That's called the breakaway current. And then the power starts out pushing hard, and it quickly pushes harder and harder until it breaks over right there. That's called the breakover kW, breakover torque. And then it starts to operate at normal speed during the strokes. And so we can use this current and voltage to calculate the line losses. We can use the current to calculate the thermal loading of the motor, and we can use the kW to calculate the net torque on the gearbox. So here is an animation plot again of the same strokes, and strokes are full, and what I'm plotting at the very top is the net gearbox torque, mechanical net gearbox torque, and the power over here, the kW, and notice how well they match. And the power is doing exactly what the gearbox tells it to do. And so that's a match. And so all that means is that you can use the power to calculate the torque, or you can use the dynamometer card and the position of the weights, or the CBE test, to calculate the net torque and get very much the same results. And since this peak right here is higher than the peak over here, it's weight heavy. And you can see here that this is the green is the current, the amps, and the red is the voltage. And the voltage is changing throughout the stroke because the amount of current flowing is changing throughout the stroke. And so when the current flow increases, the voltage drops. All right. Now, the idea of saving power when you balance a unit is because you reduce the peak torque and make it more uniform. And so once you lower the peak torques on the motor, you have less power delivered by the motor, you have less current, and then there's less current going through the motor, heating the motor up, cyclic loading, and that less heating results in a lower cyclic load factor and a reduction of your power cost. And so that's the idea of saving power. So here is a plot of the green curve is the net torque in balance, and the red curve is existing. And so if you look at this peak right here, this peak is lower than that peak. And so it says the gearbox torque rating is 320. The upstroke peak is right here, 228. The downstroke peak is 286,000 inch-pounds. And if we move the weights in from their current location, 5.9 inches, then we'll balance the upstroke and downstroke peak torque. And that's what that's saying. And here's the, if you're wondering about the equation, the relationship between net torque and kW, we can use this equation. And there's a conversion factor, an efficiency of the electric motor, the speed variation in strokes per minute. So that's the strokes per minute right there in speed variation. If you click on this little button here, we have the efficiency of the motor is 80%, and the speed variation here you could type it in, but I think we may have set this to actually calculate it, or we will set that in the future to calculate the speed variation. And you can also type in the weight of the weights to be moved. So you don't need to know the API geometry or anything about the crank angle. You just know the weights that need to be moved. And we're going to assume that the efficiency is about 80% upstroke and downstroke, which is a good assumption. And that allows us to calculate the torque based on the kW. So it's a pretty quick and easy test. It's very easy just to hook your power probes up and measure the power. For efficient operations, your upstroke and downstroke peaks should match or be close to being balanced. You don't have to know the unit description. You don't have to know the weight of the counterbalance. You don't have to know the center of gravities. All you need to know is how much the weights weigh. And toward the end of the class, we'll talk about how you can estimate what the weights weigh. All right, now we're going to talk about next is we talked about power to position the weights, and that's fairly simple. We're going to talk about using the API standard 11E. That's an API document that discusses how crank angles are related to position of the polish rod, and how crank angles are related to a thing called torque factor, that we can use the torque factor multiplied by the rod loading, net rod loading, to come up with the rod torque. And so we'll talk about that. So then we can calculate mechanical balance by knowing the moment from either the CBE measurement or the inches from end of crank of the weights. And then we take the rod loading we measure, and that gives us the position and rod loading. And along with the position data, we then come up with the torque factors based on the crank angle. The crank and the torque factors change a little bit throughout the stroke. They change from point to point a little bit. And so we use that to come up with the rod torque. So where do we get a dynamometer card? Well, you can use any of these Echometer load cells to get a dynamometer card. These are horseshoe load cells, and they're very accurate. You can use this system right here. We talked about this when we did the dynamometer presentation. Well, you can use the polish rod transducer to measure a dynamometer card as long as there's a lot of mechanical friction. You can use your own load cell with a position from either our special accelerometer or from the polish rod transducer, and those work just fine. But you can't use the polish rod transducer to get the CBE test. Only a real load cell that measures the way the rod's in fluid and measures the rod loading can be used to do the CBE load. So here's our surface dynamometer card we're going to talk about. And this is measured with a load cell. This is upstroke and downstroke, and this is the position of the polish rod versus the load. So in our database, we have many different types of pump units. And the dimensions based on API are identified. The distance from the Samson post to the Orsus head is called the A dimension. For a conventional unit, from the Samson post to the tail bearing is called the C dimension. The length of the pitman arm is called the P dimension. The distance from the gearbox shaft to where the pitman arms connect is called the radius. The diagonal distance from the gearbox shaft center to the Samson post bearing is called the K dimension, and the horizontal distance from the bearing of the gearbox to the Samson post bearing is called the I dimension, and those are shown right here. And there's a thing called structural imbalance, and if the structural imbalance is positive, then that means it's going to make the rod loading lighter. If it's negative, it's going to make it heavier. We'll talk about that a little bit. And there's a bunch of parameters here about your pump unit: the type of unit, the direction of rotation, This description, the gearbox rating, the speed, the polished rod stroke, the moments that's going to be used in the calculations of net torque or the CB load, the bottom and top of the bottom of stroke crank angle, and the top of stroke crank angle and the bottom of stroke crank angle. So if it's going counterclockwise, which this is going counterclockwise, then when it's rotated from 0 counterclockwise 357 degrees, then that's going to be the top of the stroke. That's the top of the stroke. Well, I said it wrong. That's at the very bottom of the stroke. That's when the polished rod position is at the very bottom. All right, so this is the database that we have, that when you click on select pumping unit, this pops up, and you can go in and select from various pumping unit types, classes, manufacturers, descriptions, gearbox ratings, and there's the dimensions. And here they're shown for this unit that we selected. This is the 320D 256-100 pump unit that we're using for this well to calculate the rod torque. And so this is just a little picture here that says you weigh the rod string, and that becomes the net well load if you know the structural imbalance. And you use the torque factor. The torque factor is like a torque length of the torque wrench. And so I put this here to make you think about a thing called the torque factor. If you take the length of the torque factor times this force, that becomes the rod torque. And so all the torque factor is kind of like the length of the torque wrench for the force that's being applied to the end of the torque wrench by the pumping unit times the torque factor, which is kind of like inches of length, gives you the net rod torque, or the rod torque acting on the gearbox. And that's based on the geometry of the pumping unit and direction of rotation. So here is the surface card, and this green curve is the torque factor, and you can see how it starts close to 0 at the beginning of the stroke, and it gradually increases to near a maximum about halfway up, and then it decreases to the top of the stroke, and then it increases more negative on the downstroke, and then to maximum around halfway down. And so if you look at that point right there, that's where the peak torque occurs for this conventional well. And the peak torque is the torque factor, the torque factor right there in green, times the rod loading, and net rod loading, and that gives us a rod torque. And so that's how the software takes every point you acquire and does this calculation for every load point you acquire to come up with the rod torque. And so the net well load is the dynamometer load you measure minus the structural imbalance, and you get the rod torque is that net well load times the torque factor. And you can plot the torque factor if you're interested, because this is an analysis plot, and you can see how the torque factor impacts the rod torque. And that's a feature of TAM on the analysis plots. Now this is talking about the counterbalance effect. And if you measure the counterbalance effect with a horseshoe load cell, and you reduce the load that you measured by the structural imbalance, then you can calculate the moment based on the torque factor at 90 degrees. When we stopped at 90 degrees to measure the CBE load, and you have to divide by the sine of the crank angle. Now this thing called tau is the phase angle of the crank. We'll talk about that more in a minute. So here is Ken out at the V11 well, and he's going to stop the pumping unit on the upstroke with the crank level. See, it's perfect job Ken did right there, perfectly level. And then he's going to make sure he stopped at level. And right now, and that's upstroke, and the pump is slipping fluid, and the pressure across the pump is decreasing, and so the fluid load is dropping, and Ken starts to release the brake just for an instant, and the cranks want to go up, and Ken pulls it right back because the rod load's too heavy, and so he released the brake again, but not enough, because he's watching that brake drum. When he starts to release the brake, if the brake drum moves, he pulls right back. And at some point in time, he's going to release that brake I'll pull it back. And the effect of the counterweights compared to the weight of rods and fluid and the remaining pump load will perfectly balance right there. And then we note that point, that time, and then we can determine the counterbalance effect load with our load cell. And he started the pumping unit back up. And so this is the data here. It's pumping along. Right here, this is lapse time. This is load. And there's a stroke, stroke, stroke. And he stopped on the upstroke with the crank perfectly level. And it's dropping off. Why is it dropping off? Well, because the pump has a gap between the plunger and barrel called clearance. It's slipping. And there he popped the brake right there. And then he kept on watching it. And then he released the brake and said, aha, it matches. It's level. It's not moving. So we know it's that time. And that time becomes the CBE load that we can then use to calculate the counterbalance moment from the CBE load. All right, so that's the CBE load test. So how does this test have to work? Well, you have to have a brake that works. And I've been on wells more than a few times where the brake doesn't work. And the effect of the weights at the polish rod needs to be between the trailing valve load and the standing valve load. So when the pump leaks the load off, fluid load off, that you can catch it and balance it with the effect, the CB effect at the polish rod, and the pump can't leak too fast. If the pump leaks too fast, you can't catch it. So those are the tests that we talk about. Those are the three things that are required to make the test work. Now, we're still talking about mechanical torque, and the CB test, all it was for was to come up with this load that we can now calculate the moment from the weights and the cranks around the gearbox. And we're going to use the moment now, along with the rod torque, to calculate the net torque. So we can figure out if the weights are causing to overload the gearbox. This just sounds complicated. So here is an example of a crank and a master weight. And you would take your tape measure from the end of the crank to the leading edge of the weight, and that would be the distance from end of crank for master weight number 1, if this is a crank that's closer to you for crank number 1. And you have to do that for all 4 master weights and the auxiliary weights. And then we sum up the weight times the distance to get the moment around the gearbox shaft center. And so here's a simple example where we have an 8495B crank. It's stamped on the crank for this Lufkin well. That's crank number 1. Crank number 2 is the same. Usually they're almost always the same. I can't think of a reason why not to have the same crank, because if they're not the same, it's going to cause damage to the gearbox shaft. And then we have the master weights, or 3 serial master weights, and this is the master weights on top of crank number 1. This is master weights on crank number 2. And the distance here, let's take the distance from the gearbox shaft center to the center of gravity of the master weight, and that gives us inch-pounds of moment. And the software does this automatically, so you don't have to worry about this, but there's the same calculation for all 4 master weights. And then you take the inches to the center of gravity for the crank and the weight of the crank. So take the weight of the crank times the distance to the center, and that gives you the moment from each of the cranks. And you add that all up, and it's about 500,900 inch-pounds of counterbalance moment. So this is the software in TAM, the software. So you don't have to worry about that math we just talked about. That's just showing you how it's done. And so they're not really, see, look, I used 40 inches for in the crank. Well, they weren't really 40 inches. 39.5, 40, 39, 39.7. And so the software calculates the moment from this crank, and it calculates the moment from this master weight, whatever master weight that's on there, and how far it is from the end of the crank, and it adds all these 4 master weights up, and that becomes the weight that you're going to move, the weight of the counterweights that you can move, and that is the counterbalance moment based on the actual locations, not the estimated 40 inches that we talked about just a minute ago. So this software automatically does this. You used to have to measure the distance and select your weights and cranks. If you have trouble identifying them, then you can probably contact Ken, and he can help you identify your weights and cranks on your pumping unit. Sometimes he might say, we need to get the catalog, pumping unit catalog from the manufacturer because we don't have those weights in pumping unit in our database. All right, so here, now we have the moment, either from distance from the crank or from the CBE, that's the moment. And we take it times the sine of the angle. So look, here is the green curve is the moment times the sine of the angle. It looks like a sine wave. Well, that's what the sine looks like. And then you need to add in the phase angle if the crank is bent or the holes aren't drilled along the axis of the crank. Okay, so there's the rod torque in red and the counterbalance torque in green, and the difference is the net torque. And so here's the net torque. So the net torque is the rod torque minus the counterbalance torque. And so the red minus the green equals this. And so here's our net torque. And now finally we can look at the net torque curve and say, oh, this peak right here is higher than that peak. So we're weight heavy and the weights are too far out. We need to move them in toward the gearbox shaft center. Now this calculation, what we've just seen, is pretty complicated, and it does it for every point. If you had to do this calculation, you would not like it because there's so many calculations that you have to do. So it's a lot. It's one of the reasons why, if you sample at a high speed to see a tag or a sudden impact load, then it slows TAM down a little bit because TAM has to do all those torque calculations for every data point you picked, and there's a lot of them. Now this is a kind of definition of this equation. Net torque is the torque factor times the net well load, which is the measured rod load minus structural imbalance. It says if it's negative, the horse's head would fall and become heavier. M is a counterbalance moment either from CBE or from distance from weights from end of crank. This is the crank angle, and this is the phase angle. And this slide right here came from Jim Lee. Same equation, but he's got little notes to it. Here's the torque factor, and here is the dynamometer load. Here's the structural imbalance, and then there's your moment based on the CBE test or the distance from end to crank. And then here is the crank angle that comes from the position. We know the position, we can determine the crank angle. And then here, if the crank is bent like a mark unit, it's got a phase angle. That's a phase angle. Or if it's a reverse mark, it has the holes drilled at an angle, and the crank's really big and tall, so you can get a bunch of holes at an angle along the crank. We'll see that in an example here in a little bit. Now, this is a calculation just for every 15 degrees. And look at all these columns. Look at all these rows. It's a lot. It takes a long time to do this. And so a long time ago, when computers just began, this is how we do it. We would find the crank angle for every 15 degrees and calculate the, well, first of all, we'd check for phase angle. We'd take the sine of the crank angle, and then we take the rod loading at every 15 degrees. We'd pick it off the curve, and then we'd subtract the structural imbalance, get the net rod load, and we have to determine the torque factor, which is tough. A bunch of calculations wouldn't, or pick it off the chart. And then the torque factor times the net rod load will be the rod torque, and then the counterbalance moment times the sine of the phase angle plus the crank angle gives us the counterbalance torque, and the difference is rod torque. And then we could plot it and look and see what the net torque curve looked like and say, aha, that peak right there is higher than that peak. We're weight heavy and the weights are too far out. And then we can figure out how to move the weights. Pretty difficult, a lot of calculations here. So this is a complicated sounding problem, but the software makes it easy. So even though I've explained how this works, all you got to do in TAM is either find the weights and type in the distance from end to crank, or do a CB load and use a CB load for net torque calculations, or just measure power, and that's really pretty simple. All this other stuff is I've talked about, just kind of information. And so once you have gone to a well and you measured the power and you measured the counterbalance moment or the CB load, then you have two curves. This is the red curve. This is on the torque report in TAM, and this is the red curve's mechanical, and the black curve is the power net torque, and they should show the same thing. So anytime you go out to a well to study the torque on your gearboxes, you should try to use at least two methods and make sure they agree. If they don't agree, then there's something wrong with the loads that you measured, the structural imbalance, the unit geometry, direction of rotation, the rate, the stroke length. Something's not right. So they ought to match up really well. That's why I recommend, if you're going to do torque, do two. If you can't do two, you should have been practicing already with two, and then just use one. Just use one, and you'll be okay. But it's always good to have two to check. So here I'm showing you the net torque. Here is net torque, and when you balance it, and this is counterclockwise rotation, and I'm using the counterbalance moment that we got from distance from end to crank. Then if you balance it, these two peaks are equal, and it tells us how far to move the weights to balance the net torque on the gearbox. So here's the report, and the report says to balance the gearbox torque, we need to move 5,308 pounds of weight in toward, from where they are, inward 3.14 inches. And then that changes the counterbalance moment by 16,700 inch-pounds of torque. So by moving that much weight, that many inches, 4 of them, then that's going to give us the change in counterbalance that we need to balance the pump unit. Now notice that the cyclic load factor actually went down. And so here's balance and here's existing. That means we're going to save some power. And the percentage change here is a percentage reduction in your power bill that you'd make just by putting the weights in the right position. The permissible load diagram says currently it's not overloaded. And if you balance it, it won't be overloaded. And so now you debate, do I move the weights and reduce my power bill? How much does it cost to move the weights? How much power savings am I going to have? Well, this is about a 3% reduction in power. You know, if you take that right there, that's probably a 3% change, maybe a little bit less than that. But anyway, it would be a small amount. Would 3% power savings justify moving the weights? Well, maybe you wait until you service a pump unit and have them move the weights. So anyway, the 3% power savings may not be enough to pay for the cost to move the weights. But if the gearbox were overloaded, you'd have to move the weights because you damage your gearbox, and the pay for a new gearbox is extremely expensive. Now this is a well out in West Texas, and you can see that we did some net torque calculations, and we marked on the gearbox, we marked on the crank where the weights are, and then we marked where they should be moved to balance the gearbox loading. And so I really like this. I like this idea. Put a mark on your crank so you can see where they were and where they're supposed to be. And when you come to this well next time, you can see that the weights have been moved to balance position. So that's a good, for me, it's a good technique to mark. As the mark will stay until they paint the unit probably. And some wells they don't paint them for a long time, so you can see that they're probably imbalanced by just looking at these marks. So motor power is pretty simple. 80% is a good efficiency when your peak loads occur on the upstroke and downstroke torque loads. The NEMA D motor is generally efficient over a wide range, and so 80% is a good number for a NEMA D motor. Some motors may have a different efficiency, like a NEMA B motor or ones that have been rewound, but they probably be close. Surface efficiencies. So if your surface efficiency is low due to a bad bearing, that may make you put the weights in the place that's required by the horsepower loss due to a bad bearing. So you should also look at your surface efficiency and make sure your surface efficiency isn't low. If your surface efficiency is low, you need to identify the problem and fix that problem before you move the weights. What's the best method? Well, the mechanical method is somewhat complicated. Nope, that's what you probably think. The software makes it a lot simpler. The power is easy. Recommend that most of the time you use both methods, power and mechanical. And the plots should overlay and they should show the same thing or close to the same thing. And that way you'll be confident that when you move the weights to balance, it'll be based on the combination of both the power and the mechanical method. But sometimes one method can only be applied. So you may have a gas engine, which means you can't use power. You may not have the pump unit geometry in the database. So there's different reasons why you might be able to only use one method. So this is a summary slide right here. This is getting close to be about, I guess we got one more slide. When you balance the unit, you'll have a little faster speed. Your power requirements will be reduced a little bit by balancing it. And if you haven't ever balanced your wells in a field, and only used an amp meter or something like that, then we've in the past fields like that, we've gone out and balanced them with the Echometer system, and we've seen a 10 to 12% power savings by balancing them based on motor power or torque. The KW is directly related to the pump unit. The signatures of the pump unit depend on the type of unit. We'll talk about that in a little bit. We use it cyclic loads to calculate. Now, this idea of peaks and valleys, some people say that there's 2 peaks and 2 valleys for a torque plot. And that's only true for a conventional unit. The other types of pump units we'll see have a different net torque curve. We'll talk about that. But it's somewhat easy to identify the pump unit based on the net torque curve, and we'll discuss that when we look at the examples. All right, so that's time for some questions and answers or whatever session.
Yes, we have some questions. Thank you, Lynn. And there is one question related to slide number 11 on the Gearbox Live. And the question is the Gearbox Live assumes 24-hour working, or there is a correcting factor?
Well, torque doesn't really depend on whether it's going 24 hours or not. It depends on how much the speed varies. It depends on if the pump's full or not. It depends on if the stroke that you're monitoring, if the pump fillage is the same pump fillage as when you set the weights. So it doesn't matter that much whether it's on a pump off controller or on a percentage timer. It only matters if the pump fillage has changed. If the pump fillage changes, then the net torque changes.
I think it was related to the Gearbox Live on the Lofkin plot.
The same. That's a good question. It really relates to overload. And so if the gearbox is overloaded, it's going to reduce the life, whether it's on a percentage timer or a pump off controller or just on hand. So you just don't want to overload the gearbox. You're going to reduce the life. And I think it's gradual, but maybe the percent run may have an impact. But I've seen fields that have pump off controllers, and if they don't balance their pump units, their gears are failing. Their gearboxes are failing. So I'm not so sure I would worry about if it's on 100% run or not. I'd use that to identify potential failure.
Good. Another question referring to the power probe installation and the power measurement is, in most oil companies, it is mandatory to have a certified operator in electricity to take these readings. Is it really mandatory to have a certified person?
Well, that's why on the wireless power probes that we developed a fixed power adapter. So then you take a certified electrician, have him go put the power current sensor and connect the wires, and then whenever you come up to the well to do a dyno, you just plug into a connector on the outside of the panel and not open the panel, and there's no need then to have a certified electrician. So if you have to have an electrician come with you to the well, that's going to be an added cost. So ideally you would want to If that's a requirement, have them install the fixed power adapters, and that'll eliminate that issue.
Okay. And there's more open question here. Probably anybody who's actually receiving or supplying this kind of service may answer. And the question is, what is the cost, let's say a ballpark number, cost of moving counterweights on a pumping unit in West Texas?
Yeah, my knowledge is kind of old. It used to be about $125, but I don't know what it is now.
We have another input from Kansas. It's about $200 an hour, and the job usually takes between 1 and 2 hours based on the pumping unit size.
That's probably a better answer than me. That's a good answer.
But anybody who's participating in the class may better answer that question for sure. And in the slide 45, I think, and there are two questions related to. I'm just going to make one of those. From Andres is asking, is power data more accurate than dynamometer data in order to properly balance a pump jack? Are they complementary methods, or you could lean towards either one of these ones?
The CBM method, where you measure distance from the crank, is very, very accurate method, and the power method is very accurate. Now, the power method is more accurate than the CBM method if the unit has a different geometry. So I mean, that's why you want to try to do the power method and the mechanical method together, because the power method is a check. Now, if the unit's way out of balance and the efficiency is not going to be 80% on the upstroke and downstroke, you may have to do a double, move them once and then move them again if you have power. Because efficiency is assumed to be equal on upstroke and downstroke efficiency, and that's generally true, but sometimes with way out of balance it won't be 80%, it might be less than that. So my preference, I like, if you read the paper you'll see that the CBE method was the least accurate of the two methods, and so that's what the best method paper talks about. I think that if you do enough CBE tests and learn what it takes to do the test, then maybe the CB method can be just as accurate, but it's a mechanic. It's a person doing the test versus just using a dynamometer card with the distance from end to crank, which is easier, probably more accurate than just doing a CBE test and trying to stop it with the weights level. And there's probably other things that affect that, like static friction may affect the CBE test.
Probably on that, Hector at the beginning was asking how much weight the brakes take from the polish rod.
Well, if the brakes aren't dragging, you mean doing a CBE test, how much weight does the brakes take?
I want to assume that the question is just related to the CBE test.
Yeah, so if the brakes have a decent spring on them and they pull away from the drum, then they don't take any or very little weight off the brake. But if the brake shoes contact in the drum and there's some kind of mechanical contact, then it's going to have an impact on the weight. So it's not supposed to have any load if the brake's released.
Right. Just considering on the CBE, we want to read the value with the brakes non-applied.
Yeah.
With the brakes released. The other question is again for which method is more accurate, and you already covered that. And another question is how effective is the CBE method when performed on a well with leaky pump?
Oh, it's really hard to do the CBE method on a leaky pump because you can't balance the rod loading and the weight rods plus weight rods and fluid. Weight rods and fluid is constant, but the pump load is changing really fast. So you can't release the brake and catch it and determine the balance. So it's almost impossible. So you probably can't do it because it leaks too fast.
Anthony Allison has been, I think he has a comment on the Gearbox Live plot, and he says, I think Cecil assumed constant operation at a given RPM on the gearbox, but I'm not sure what the RPM was used. And He also says that there has been some empirical values for the cyclic loading factor published by Unigeometry and prime mover type. Have you ever compared these measured cyclic load factor values to see how they compare?
Yeah, we use the cyclic load factor to calculate the motor size, and the cyclic load factor is based on the RMS torque compared to the average torque. Now, the more the torque is not near the average, the higher the cyclic load factor becomes, and it has more potential for the higher the cyclic load factor means you're going to have more power. So the other question he had is a little different. So when Norm Hind did a presentation sometime in the past at the short course, there's a paper he wrote that said about gearbox ratings for certain speeds, and most gearboxes are rated for like 25 strokes a minute without any harm. So there's not really any speed limitations on the gearbox. The real issue about the gearbox and the cyclic load factor is you don't want to have a high cyclic load factor, because that means you're going to have more power. That means that the RMS torque is much farther away than to the average, because the cyclic load factor is RMS torque divided by the average, and that means you're going to be spending a lot more energy heating the motor and a lot more energy, more horsepower. So yeah, I would expect to have. Anything I've done a long time ago. I haven't done it recently. I only did it when I had my own pumping units and Framrod AS. It's been I'd say it's been probably 30 years since I looked at that. So it's been a long time.
Uh, Probably a question that needed some clarification from Orlando about the sensor. He's asking what sensor is more accurate for measuring torque values.
Well, if you're talking about the load, you need to use a horseshoe load cell, because the PRT, when you're trying to calculate the rod loading, is shifted based on mechanical friction downhole. And so when you use the PRT, the surface loads are not as accurate as the load cell loads are. So a donut load cell, a horseshoe load cell, will give you more accurate surface loads for the rod torque. Now, if you're comparing the net torque for power versus the net torque for mechanical calculations, this curve right here shows, look how close they are. They're in good agreement. And so normally the net torque from mechanical and the net torque from power overlay, and they look like they both are saying the same thing. When they start not matching, there's some kind of problem. So
Good. And always remember that you cannot perform a counterbalance effect, a CPE test, with a PRT. You can do that only with a load cell.
Oh, right.
Juan's asking, the units that are not in the system library, can they be entered, like dimensions and weight?
Yes, you can. Well, hold on. You can currently type in the API dimensions and structural imbalance from a manufacturer's catalog, but to put in the pumping unit crank weight and the counterbalance is hard and difficult, and we need the information from the manufacturer to type that. Echometer needs to type that in.
Yeah, unit libraries is modifiable. You can edit it by adding units, and you will need the dimensions. Crank and counterweights is a different story.
Yeah.
Anthony is asking, can you comment on the quick and dirty current measurement that many people use for checking balance compared to power, KW?
Well, when you're using the amp sensor, an amp probe or an amp device that measures amps, you're looking at it, and it has to be fast, and it has to be, and you see that the two peaks don't match, and you can move the weights based on what you're seeing, but in some wells it can be so out of balance. When when the weights are falling, they can generate enough power to make a generated peak and a peak lift where the motor's providing the lift match up. So in some cases, you might pick the wrong peak. In a mark unit, you have 3 peaks. We'll show that in a minute. So there's not always just two peaks. So it can be difficult because you have to get the upstroke peak and the downstroke peak. So it's
Yes, it's much more accurate when you have a sensor that
that's
measures at a much higher rate.
That's one of the reasons why if you go out and rebalance it with a actual system like what we're talking about, you'll see a reduction in your power bill by 10 to 12% because it's just not that as accurate as you'd like.
Okay, one more question is the wrist pin weight taken into consideration when calculating counterbalance at different stroke lengths?
Really, what we're assuming that the structural imbalance takes care of that. So the wrist pin is attached to the pitman arm, and that's not part of the crank. Yeah. So we're just doing the counterbalance moment from the way of the crank and way of the weights, and then the wrist pin should be it's attached to the pump unit, and that's all handled by structural imbalance. So the wrist pin weight doesn't matter. It's somewhere else.
Just the crank and counterweights.
That's correct. That's it.
Yeah. So Anthony, based on your previous comments, people agree should stop using amps. Amps. Yes, we have seen a lot of difference. I mean, just by looking at a screen, blinking about half a second apart, has a very low sampling rate. And when you compare that to a chart that you're acquiring at least at 30 hertz, of course you have more data points and you can check torque peaks much better or current consumption much better than what you can do on a single screen. Of course, it's much better to do it with these kind of devices.
Yeah, and I'm not sure if you really want to use amps when your gearbox loading is close to the gearbox rating, because if you use amps and your gearbox is still overloaded, then you're going to spend a bunch of money for a damaged gearbox. So I've been in meetings where the gearbox failure is a problem, and they were using the amp method, and they were having lots of failures. So, and they were pointing fingers at everybody. They were pointing fingers at the people that service the pump units. They were pointing fingers at the people that design the positioning, the weights, and everybody was mad at everybody. And they were using amps. So that was the problem, and I'm not sure they fixed it.
I'm just checking. I don't think I have any other question, kind of repetitive questions on the accuracy of the different methods. And
all right, so
you can start with examples.
All right, let's go into the examples. And so on the end of the presentation, I've added a few more slides, and I did that so I could try not to forget stuff. And so when I go pick a well, and I go to my database, the pick a well shows that when you install those files, it will install them on your computer in a folder called Echometer Online, and there's going to be a net gearbox torque 2020. This is the 12th Ask Echometer, and we have 1, 2, 3, 4, 5 examples. And so the first example is I'm going to look at is the V11 well, which is a conventional pump unit. It's not overloaded, and I'm just going to go through and show you some things about the software. So I'm going to open that up, and so here's the V11 well, a surface card and pump card, and we're looking at a well that we used. In this case, the polish rod transducer, we use the pressure transducer and the power probe, and this one uses a horseshoe load cell. So let's stick with the horseshoe load cell. And the CB, if you look at this, I've got the permissible load lines drawn on the surface card. And so if you go to annotations and you click on annotations, we have added an option to show permissible load lines as an option. And so if you check on that, it turns it off. You turn it back on by checking it. And you can also show that in report if you're concerned about torque loading. So that's a quick way to show someone that their pump unit's overloaded. In this case, it's the unit's not overloaded. It's just not perfect balance. If you're interested about the CBE load test, Dr. Podio's presentation is in the July 15th paper that we did on Ask Echometer. If I go to the history button right here, the history shows me the previous tests I have on this well, and I just have a couple days. March the 12th, and I think there's a March the 13th data set. And we're looking right here at the March 13th data set here. If I were to go click on a different well, it's a different day right here. Let's look at, here's 51 strokes in this data set here. If we click on this one, that one's no power, so let's click on this one, and that has PRT, so let's click on this one, and this is a PRT, so I'm going to stay with the one that's most recent because I want to look at the one with the horseshoe load cell. So if I look at the event viewer right here, I can go to the very first part of the test and see that stroke number 2 is a full dynamometer card. And if I scroll over to the right and go to stroke number 17, I can see stroke number 17 has an incomplete pump fillage. And so why does that matter? Well, let me show you why. If I click on the field view and I hold down the control key and I go click on stroke number 2, it's going to overlay both strokes. And so now stroke number 2 is the green one, and stroke number 17, incomplete pump fillages, is the black stroke. And what you see is that when the pump has incomplete pump fillage, notice that the minimum load moves from that point to that point, and it's actually lower. So we have a lower minimum load when we have incomplete pump fillage, and it's a different location. And so that means that the torque loading is going to change. So we would have, if we set the weights based on a full card, then the torque loading, the gearbox could be even overloaded, but it's probably not, because this load line here didn't cross those the permissible load lines. But in some cases, you can get, depending on type of unit, a big negative load or much lower load here, like a mark unit. All right, so that's to look at different loads, permissible load lines. If we go look at the torque, let's go look at the torque report. So I'm going to go to the report. Let me move this over here and go to the report. And I'm going to look at, right now I'm looking at stroke number 2, which is a full card. And I come down here and look at this. So this is stroke number 2. And if I select stroke number 17, I'll click on this button right here and change it, then it's going to show me the torque with stroke 17. Now, what I'm wanting to show you though is that the balancing changes. If we look right here, that the maximum downstroke peak existing is 260 with the incomplete pump fillage, a higher net torque. If I go back to stroke number 2, let's go to stroke number 2, and its downstroke is 270, so it's even more. So the full card has the highest torque, even though the minimum load is less for the pump that's not full. But sometimes it'll swap. So you just need to be careful and cautious about your gearbox overload, because by going from full to pumped off, you may even overload your pumping unit. All right. If we go back to, we've already talked about this. If you look right here, we're looking at the field view. If we go to the details view and we go to annotations, and I want to display the power slider, there's an option that's for the power slider. And let me see, power slider right there. And so now, if we measure power and we move through the stroke, we'll see this little red dot in sync with the dot on our surface card. So as I move to the right on the upstroke, the power required to lift the net torque on the upstroke is going higher and higher. And then right there's peak load, and that is all right about there is the peak torque. See right there is maximum kW. If I keep on moving on the upstroke over there, I'm generating some power here. It's right there. It's less than 0. And then when I come back on the downstroke, when I get to right about here, that's where the peak torque on the downstroke occurs. And so that's kind of, to me, that's provides information. It lets you understand the torque loading by looking at the kW. It's the same as net torque loading. We're looking at the surface card and the pump card and using that slider. If we go back to the report, let's go back to the report here. This is if we look at the top, it says torque and it says power. And so if we got both of these checked and we've identified and we selected the show the net torque and show the power, this says move the weights in based on this difference in peak torque, higher peak torque on the downstroke, less peak torque on the upstroke. So we're rod heavy, the weights are too far out, we need to move them in 3.14 inches. And that's what this is telling us. And it's going to change the counterbalance moment by 16,700. If we scroll down to the next report, that is the power. And the power says move the weights in about 5.9 inches. So it's a little bit different between the two. One says 5.9 and one says 3.14. So you I would say you move it based on the average, moving about 4 inches would probably be correct, because that's what they're both saying, and you probably then find that you're pretty well balanced. So I wanted to show that. Oh, if I go to the power analysis, the power torque analysis curve plot. So this is a conventional pumping unit, and this is the power torque calculations for a conventional pumping unit. And what I want to show you though is that when you have a conventional pumping unit, you have a peak net torque on the upstroke, you have a peak net torque on the downstroke, and you typically have a valley in the middle where most of the power is generated when the weights swing through the bottom. And then you have sometimes another little peak between after the upstroke peak. So this is created by the rods making the motor spin faster than 1200 RPM. So when the kW drops below 0, that means that the motor speed is going faster than 1200 RPM and it's generating power. So this is a typical net torque curve or net kW curve for a conventional pump unit. All right, now if I click on Edit and go to Edit, I'm going to close out this event viewer. Well, it's going to stay. That won't matter. Now, there's a quick view and there's a detailed view. The quick view just shows you a little bit of data about the well and the detail and what you need. I guess what you need, but there's more information displayed on the detailed view. We're going to go look at the list system. Is where our pumping unit information is. So if we go to the list system, we have two tabs that relate to torque and power. There's the tab here for the pumping unit and surface torque. We have a tab here for the electric motor. So here's our electric motor information, our horsepower, and our runtime. And then here is your pumping unit information, your Lufkin pumping unit, the surface stroke length, direction of rotation, and we're going to use the counterbalance effect counterbalance moment from the weights we positioned based on this button right here. So we're using the counterbalance moment, and here's a couple of CVE tests that we've done in the past. And these are, we did these two 218 and 313, and they both have about the same counterbalance effect measurement. So the first thing I want to do is click on the select pumping unit, and that goes out to the database, and it shows you the pumping unit that we've selected for this well, and it has you know, some comments. It has the structural imbalance, maximum stroke length. It has just some information in the dimensions. Here's dimensions that it's showing. You can change the unit, you can modify it, you can use this unit to duplicate it and then modify the dimensions for your own pump unit. Why? Let's say it's the same unit, but you for some reason shifted the walking beam a little bit, and the A dimension is longer and the C dimension is shorter. So that would give you a slightly longer stroke, so you need to put that in if you've done something like that. The torque factors and the crank angles all assume that the unit is assembled with these dimensions. Okay, close this back out. And here's some short sorts that you can change and sort for if you're looking for a particular type of unit. So that's available. What else? Okay, then down here, we've talked about this, is the counterweights. If I click on that button, it brings up the counterweight screen, and it shows us those master weights are positioned based on actual distance from end to crank. And there's no auxiliaries. There's the 3 serial master weights. There's 4 of them. There's master weight 1 and master weight 2 on the crank number 1, 8495B crank, and it's a Lufkin manufacturer. And this one is crank number 2, 8495B crank, with the same master weights in a slightly different position. And if you change the position, like from 39 to 42 or whatever, then it's going to change the counterbalance moment. The weights will stay the same. So if I go back and change it back to 39, we'll see that 499 should be reduced to 39. Let's say 39. We'll tab out of the field, and actually it says it went up. So that should counterbalance moment. Oh, we made it farther in, so there's less moment before. So this distance from the end, I made it 43. That means the weights are farther in, and that means that this should go down. And if we put it back to 39, it should go up because they're farther out on the crank. Okay. Okay, so that's this well right here. It's a conventional unit, and let's see, save it and close it. And we've reviewed the report. The report shows torque, net torque. It shows where to move the weights. Okay. The next example I want to show you is a reverse mark. And so if I go pick a well and go to the reverse mark, this is a well that we went to quite a while ago. This data was collected in 2001. It's a well up in near Vernal, Utah, and we didn't use the power probe because it had a gas engine, so you couldn't use the power probes. And if we look at this data and look at the event viewer, the first card is not very full, and the last card is a little less full. If we go to the next one, the first stroke is fairly full, and then as we move to, from the first stroke to the last stroke, it still is gas interference, but See, it's almost full on stroke number 1, and then as we move to the right, it becomes less and less pump fillage. All right, so why'd I come here? Well, this is a well that that was included in the paper back in the paper that we wrote in 2004 on the best method, and this is a well that had the gas engine. And what I want to show you though is that when we imported this data into the TAM software, the pumping unit data was lost somehow, or it got lost somehow. I'm not sure how it got lost. So if I come down here and click on counterweights, this information is missing. And so the unit description is it's a 395. And so if I go into the crank it's a Lufkin crank, and the weight, the crank arm is 901. Let's go find it. 901 RM for reverse mark. Okay, that's the crank, and so they're both the same. And we had OORO weights, and they were positioned at the end of crank. And so we'll say done. Okay, and that says that matches ORO. Oh, there's some auxiliaries. There's some OOS auxiliaries on here too. And they all have OOS auxiliaries. Okay. And so that's an example of putting the weights in into the program and say done. Okay, now if we go save this and look at the net torque curve. So if I go into the report and look at the net torque curve, so you can see here it looks like it's currently overloaded, and we need to move the weights based on this dynamometer card. If we go back to stroke number 1, we'll probably find out that it's not quite overloaded. It's still overloaded. But you can see it just almost doesn't fit in here. It's overloaded by what percent? Let's just find that out. It's overloaded by about 15%, which is quite a bit. So that's going to significantly reduce the life. So this I think if we were operating with a full pump, we'd probably have not have an overload. But I don't have data to show that. Now, what you want to notice though is that when I talk about the conventional pumping unit, you have two peaks and two valleys. Well, if a reverse mark, it's different. Look, it's got a valley here, a valley there, a valley there, and it really depends. It really depends on the geometry. And so for the reverse mark unit, if we look at the reverse mark unit as a, let me pull this slide over here just for a second. So here's the reverse mark unit, and this is the reverse mark. If you look, the holes on the crank are drilled at an angle, and that creates this phase angle between this line and a line down the center of the crank. The reason why the reverse mark is beneficial is that when you, let me escape back out of here, when you have a properly balanced reverse mark, you almost have each of these peaks the same height, and you almost have a constant torque, and it'll be a little more efficient than a conventional unit by having almost constant torque. So this is a advantage. The reverse mark has an advantage. This big hump in the middle is due to the phase angle, and that's the reverse mark. And so this, we just demonstrated putting the weights and cranks in, and we we see that it's overloaded, and it says that we need to move the weights in. Move the weights in about 17.73 inches, so quite a bit to balance it. Okay, the next one we're talking about is a mark unit, and the mark unit is an interesting example, and this is an example that we've had for quite a while. And if you look, the mark unit, here's the crank, and the crank's bent, and so again, the angle here versus the center line is the phase angle. And we need to talk about and show the polish rod velocity, and talk about being fast on the downstroke. So the mark unit, the advantage of the mark unit is typically if you put the gearbox inside the frame, the structure of the pump unit, you can typically have less horsepower and have less smaller gearbox. The disadvantage is that the fast downstroke, and if you have incomplete pump fillage, then it even increases the speed on the downstroke, which was going to cause additional rod on tubing wear. And so I'm not a big fan of mark units unless if I can't keep the pump full of liquid, because that's going to increase your rod on tubing wear in my view. This is just a video here of the mark pump unit, and they only operate counterclockwise, and this one's not going very fast. This is a mark unit up in North Dakota, and it's just one stroke. And so I just recorded one stroke, and I'm going to play it over and over again. But we have the data, but I didn't put the data in the presentation. But that's just an example. Let me escape out of here. All right, so let's go look at that gearbox balance. So if we go into the gearbox balance example, and there's two different data sets here. One data set, let me stretch this out a little bit here. One data set was collected on June the 10th, 2003, and the second data set was collected on June 17th, 2003, a week later. And so when you go to the first one and you look at it, what you see is that, look, this is the example we have where the rod loading during this portion of the stroke is too high and the gearbox is exceeding the permissible load, and it's overloaded right here. And if we put the weights in the right place, then the gearbox loading won't be exceeded and will be okay. So let's go look and see what's going on. So if we go to the report and look at the report, we see that this gearbox is rod heavy. The weights need to moved out 27 inches, and currently it's overloaded by it's loaded 125% of the rating, which means the life of the gearbox is only going to be 3 years. It's going to be short. All right, so what do we do? Well, we got to go move the weights. So if we go click on edit and we look at the lift system and we click on counterweights, we see that the weights are already at the end of the crank. So we need to add more weights. And so this little slide here is the same picture as we had right there. So here is the weights currently at the end of the crank, and we need to increase the counterbalance moment because we're rod heavy, and we need to go from the current counterbalance. In fact, it says right here we need to go more than 291,000 inch-pounds. And so with the existing weights right here, we're at 2,004,000 inch-pounds, which is 2,004,000 inch-pounds. But anyway, That's the existing counterbalance moment. And if we add just one OAD master weight by coming here and changing that, dropping it down, we see that the counterbalance moment goes to 2,174 thousand inch-pounds, or each OAD weight adds about 170, and to be more than 291,000 inch-pounds, we need to add 2 OAD weights, or we could add an OAS weight, and we would add 4 OAS weights would add 340,000 inch-pounds of counterbalance. So they actually, the two OAD add the same counterbalance as the 4 OAS counterweights. So we decided to purchase 4 OAS auxiliary counterweights. Now, when we did that, we positioned the counterweights a week later 3.25 inches from the end of the crank. And so this is, and then we now have an existing counterbalance moment greater than the amount that was required. And so we're no longer overloading our gearbox. All right, I think that's it. So let's go show that. So if I exit here, now first of all, let me show what we did. If we click right here and click on OAD, we'll see that this number right here changes from 2004 to adding one weight, which is 170,000 inch-pounds of torque from that one OAD weight. And we need to add more than 291,000 inch-pounds of torque, so we need to add two OAD weights. If we add an OAS weight, it's about 85,000 more inch-pounds. So we can add 4 OAS weights, or we can add 2 OAD weights. If we had 2 OAD weights, we'd have one on master weight one on master weight number 1 on the other crank. But we decided to add four OAS weights instead of just, and that would be symmetric. So let's say done and close this out and say don't save, or save, it doesn't matter because we didn't change anything. And now if we go over to the next example, the next one, and click right here, no, click right, Dyne history, and then click right here. Now we can see that, look, we're not overloaded anymore, and we're not overloaded down here. And so the mark unit fits right in this permissible load diagram with an overload. And if we go to the report, let's see what the report says. It says that, well, it's pretty much close to imbalance. It says we can move the weights about 1.35 inches in, and we'll both the upstroke and downstroke peak will be balanced. So that's an example of when you have to add weights, and that's the example you have. And we'll publish this spreadsheet here, this PowerPoint, and it'll go along like a workbook along with these examples. Now I've got a few minutes here. I want to talk about the other two examples. So I'm going to pick the Rotoflex unit right here, and the Rotoflex unit, we only can currently balance it based on power with our old software, but soon we'll have the power measurement balancing with the new TAM software. So let me show what I'm going to show here real quick. If I go to the analysis plots, here is let's put the surface card, surface dynamometer card, polish rod load versus polish rod position. There's our surface card, and here is our, I want to put the KW. Here's polish rod velocity, but I'm going to put KW here. KW. Power. All right. Now, if you look, you can see that the peak KW on the upstroke matches the peak KW on the downstroke. And what does that mean? Well, that means that this example here is the balance condition, and there's a paper that we wrote that's on our webpage, and we moved off 60 weights a certain number of pounds of weights, and now our unit is balanced. The roll effects unit is balanced. And what you'll notice is that the speed on the upstroke and the speed on the downstroke are the same. So if you look right here, let me change this to seconds. The polished lead velocity is going down 38.1 inches per second on the downstroke, and it's coming up at about 37, 38, depending on where you stop, on the upstroke. And so this is an example where the power data currently can't be used in TAM to balance it, but it can be used in TWM. So if you have your Rotoflex pump units in your wired system, you can use the TWM software to calculate how many pounds of weights to remove. That's a feature that we plan to add. And then I want to talk real quick about air balance. The air balances are kind of like a conventional unit, but not. And so if I were to plot the, let me go go to the report. And I just about ran out of time. And this is the in-balance torque, and we don't have the air balance yet to put the M&S in the database and calculate pressure required. But I want you again notice that when you look at the air balance unit, that the torque signature is different than the conventional. It's different. It's almost like a mark, but it's different. It's different than the reverse mark. So each unit type has its own net torque curve, its own kinematics, motion. And so I hope you guys enjoyed the presentation. That's the end of my 2-hour presentation, and those examples along with the talk will be on the database on our Ask Echometer webpage. All right, Carrie, I'm finished.
All right. Well, thank you, Lynn, and thanks, Gustavo, for your help with the chat and the Q&A. It looks like there are a few more questions, and so we're going to answer those, and I'll get those questions typed up in a Q&A report that'll be posted on the website along with the link for session 12. So again, we sure appreciate you guys joining us, and hope to see you next Wednesday. You guys have a great week. Thank you so much.